Yeah, come on down. You're the next item up for bids. So I'm going to say officially, happy Garbage Day, everybody. Happy Tuesday. Welcome back. We're on the downhill stretch of the semester now. It's coming. 6 weeks left. I counted. All right. So let's see here. I don't have to make sure I'm screen sharing or checking on Zoom because there's none of those people here. That's still a habit that I'm trying to break. But we've got formative assessment number 3 also, so the review topics that you mentioned in the first question. Bladimir is going to take a stab at answering those as well, right?
Yes.
Okay, take it away, sir.
Thank you, Alisa. Hi, everyone. I hope you are doing great. I missed this class. It was interesting. Last Thursday when we were at the event, I was thinking about cluster multi-level things.
Oh, you said, I would much rather be in class.
Yeah, for sure, yes. But yes, so last Thursday it was between 4 p.m. and 6 p.m. something like that. We had the posters presentation and I was talking about multi-level modeling. So yeah, good to see you again. I hope you had a great weekend. Thank you for your answers. We read them. So the first slide that I will present you has some of the questions that you mentioned, some of the topics that you would like to cover again or have more comments, and then we have the activity in which you played reviewer 2 role. So we also have some comments and thoughts to share. So thank you for that. Again, you can find these materials on GitHub. The link is on Lisa's website, and you can also find the original template in QMD format in case you want to do something like this. And I found that this is really helpful when you want to do something like quickly. Once you have the template, you change the content and then you press one button and you have your presentation ready. So I like that, and I'm including the PDF files and the QMD files in case you want to do something similar. You can customize these things as much as your imagination is. So I'm surprised with the flexibility of QMD files. That being said, first of all, here we have a short review about some things. So first things first, cross-level interactions. One of the questions that you had were related about how many cross-level interactions we have and what do they mean. So cross-level interactions, as any interaction in a regression model, we know that they are moderating the fixed effects of the variables involved. Okay? Cross-level, the meaning of that is in multi-level modeling, we know that we have more than one level. So let's say that we have data for the students in classrooms. Okay? So we know that we can have at least 2 levels there, the students in classrooms. And we have one individual outcome at level 1, which will be related to students. A cross-level interaction can help us to define if the fixed effect of a level 1 variable, the within cluster fixed effect of a student variable, can vary across classrooms. That's what cross-level interactions do. The level 2 variables will be moderating what we have at level 1. That's what they do. Although, depending on the parameterization that you use, one cross-level interaction cannot be enough to avoid smooshed fixed effects, smooshed or conflated fixed effects. Why? Because we can use something like the contextual and within cluster parameterization, in which we add the cluster mean predictor, the cluster mean of the level 1 predictor as another predictor at level 2, and we are not centering our level 1 predictor at the cluster means. So in that case, the level 1 predictor is like the original level 1 predictor, which within cluster components and between cluster components packed in the same variable. So in that case, the fixed effect of the cluster mean at level 2 will be controlling for the fixed effect of the level 1 variable. Although, if you add a cross-level interaction between those 2 variables, you will have a conflated what? A conflated cross-level interaction. Because in that case, your level 1 variable has the level 1 and level 2 information in it. So the cross-level interaction will be smoothed because your level 2 and level 1, what you think is purely a level 1 thing, is not. So that interaction can be smoothed too. Now, If that's the case, what can we do? If we have a smooth cross-level interaction, what can we do to unsmooth that?
We add another slope, right? To account for the level 2.
Exactly. And what variables could be involved in that interaction?
Variables could be involved in the interaction. Not sure I understood the question.
Yeah. So in the cross-level interaction, we will have the level 1, right? And we will have a level 2 variable. In the example that we have later, we have something at level 1 which was ability, right? So let's say that that's properly specified. We have the level 1 ability and we have the cluster mean ability at level 2. And there is another variable like group that represents intervention, and we want to include a cross-level interaction between those two variables, right? Is that enough? We said no, right? Because the level 1 could be, that depends on conflation, on the parameterization of the fixed effects, on the centering scheme. We will talk about that later. But let's say that potentially the cross-level interaction can be smoothed, right? How can we solve that problem?
Can I guess?
Of course.
You square the level 2 predictor?
That can be something, yes, but not in this case, because group is another variable. It's not the cluster mean of ability at level 2. It's another variable at level 2, and we want to see if the within cluster fixed effect at level 1 is moderated by the values of this other predictor at level 2.
It might be easier to talk about that specific example when you get to it. That way you can point
Yeah, I think so. Yeah, this is too abstract. So for now, let's say that cross-level interactions, as any interaction in a regression model, are moderating the fixed effects of the variables involved, right? Okay, how many can we have in our model? For one model, at least 1 or 2. It depends on the centering you are using. Sometimes one cross-level interaction will be enough, but to do that, you need something like at level 1, the within cluster version, or the cluster mean center version of the level 1, or the within cluster center version of the level 1 predictor. So you have only the purely within cluster component of the level 1 predictor. If that's the case, one cross-level interaction can be enough, but you are dropping the option that variables at level 2 can interact too. We will talk about that later. Questions about that? About the role of cross-level interactions?
And we'll have more on that this week too.
Yes.
Yeah, we're not done talking about that.
Yes. How do you feel with that description? Good? Okay.
We'll do this.
Awesome.
I'll go 45.
Yeah, a lot of words. I know. If you have questions, just please say whatever you are thinking about. Point 2 is values for the random effects, how to interpret these things, specifically correlations. But first of all, the numbers that we have in our output, those are the variances of the random effects. Remember, please, that the model do not need the specific random effects for each observation or for each cluster in this case. We are not using that. What we have in the model output is just the variance of those random effects, okay? Now, in terms of correlations, remember that in the G matrix, in the matrix of the random effects at level 2, we will have as many variances as random effects we are including. So in a random intercept model only, how many random effects we have in our matrix at level 2? For a random intercept only model, how many numbers we will have in the G matrix or the matrix of random effects at level 2?
They don't know G matrix yet.
Oh, yeah. The G matrix is the matrix of various components at level 2. So how many taus do we have in tau squares? Do we have in a only one, right? That number, whatever it is representing the variance of the random intercepts, right? So now, if we add a random slope, how many variance components do we have now at level 2? at least two. And what's the third parameter there?
The interaction between
Not interaction, but the covariance in our model. They will be related. So that's what correlation means here. So this correlation makes sense in a model in which at least have one random slope. Why? Because if we have the random intercept and the random slope, at least one, we will have one correlation. If we add a second random slope, now we will have three covariances, because we will have the covariance between both the random slopes and, to each other, and the correlation between both random slopes and the random intercept. Are you following those ideas?
I just have one clarification question.
Yes, of course.
Vocabulary.
Yes.
Correlations and interactions are different.
Yes, they are. Yes. In
How
this,
would you interpret the correlation?
yes, that's what I'm trying to go now.
okay.
So to answer that question, correlations and interactions are different. Interactions mean that something is moderating other thing, but correlation is just the standardized version of the covariance between two variables or two things. Okay, so they are different. Now, about the specific interpretation of correlations, because we have that whatever the number is for a random variance, that's representing the variance of that random effect in our model. Whatever that number is, and we don't have like a measure. Is 10 larger than 8 all the times? That's complicated to say. It is, like, but they don't have like a specific meaning like a correlation. 0.4 is stronger than 0.3, we know that. But in terms of variances, that's different. Now, for correlations specifically, let's say that we have something like 0.5 positive, a correlation between a random slope and the random intercept. We are saying we could say in that case that as the deviations from the fixed intercept increase, the deviations from the fixed slope for the level 1 predictor increases too, because that correlation is positive. And we have as reference the deviations from fixed effects. Right, Lisa?
Yes, that analogy works fine if all the slopes are positive. But if they're negative, then it gets harder to explain.
Yes.
But I can try later.
Okay.
I have a picture in my head. I don't know.
Yes, thank you, Lisa. And that's
And
confusing.
whiteboards.
I could use the whiteboard, but it's not captured on the
I
board.
know.
Yes.
We're gonna
Paint
get
to the rescue. I like paint.
Yeah, we're gonna get
So it is complicated, and most of the time people don't pay too much attention to those results. I've read many papers that use multi-level modeling, and they just report variances as part of the model results, and that's all. It is complicated to have an idea about how to explain and what to do with those kind of results, like correlations or covariances. Third point is the equivalence between effects. And here I'm not only talking about the fixed effects, but also random effects. I know that we are not cover random effects like too much yet, but the analytical equivalence or mathematical equivalence or likelihood equivalence, a lot of synonyms, they mean that when you have one model with one type of parameterization or centering scheme, let's say that you are using within cluster and between cluster fixed effects. So at level 1, your level 1 predictor is the cluster mean center version of the level 1, and you have the cluster mean predictor at level 2. Those fixed effects could be obtained using a within cluster and contextual fixed effect scheme via linear combinations. That's the key. So both models are analytically equivalent or likelihood equivalent
in the fixed effects.
in the fixed effects. Now, that works for the random effects too, but it's trickier for the case of the random effects. Although we can have the random effect variances from one model based on the results of the other. So using within cluster effects and contextual effects, you can obtain similar results as those that you will obtain if you change to within cluster and between cluster parameterization. So yes, that's the thing. This, for instance, is a linear combination because we know that a between cluster fixed effect could be also obtained via linear combination summing the within cluster fixed effect and the contextual fixed effect of the variable. And you will see that the estimate and the standard errors will be the same. If you have your model results, and I think that's in example 3, you have your set of results using the within cluster and the between cluster scheme. Yeah, I'm still using that word.
Yeah, I would say parameterization, but I like scheme better.
Yes, yes, parameterization is best, I think. So you can take those logs, you use a linear combination, and you will get, for instance, the contextual fixed effect, and that estimate and that standard errors will be the same that if you change your whole model to use the within cluster and contextual fixed effects, the results will be the same. To me, that was surprising because I thought that in linear combinations, we were only considering like the things that we are manipulating or using in the linear combination. And I thought that in a regression model, we were using more things. But when we compare the results of a linear combination to the model results, the numbers are almost the same, like to the third decimal place, which was surprising to me at least. Fourth, this is related to a question about can we do what we are doing here with non-normally distributed outcomes? And yes, we can. For instance, if we have categorical data, binary outcomes or categorical outcomes, we can use what we are using here, although there are some things that we will see in one, not this semester, unfortunately.
No.
Visit last version of this class to see that, but yes, what we are doing here can be used with non-normally distributed outcomes, and that's known as generalized linear mixed models. So we can use any type, almost any type of outcome in these models.
Yeah, I will say that software for generalized mixed models is hard to find. Like there's certain combinations that I have not found. For instance, beta binomial, I've never seen in a multi-level framework. And that's just that's not like a theoretical limitation, just people have made one. In cases where I need something that looks binomial because I have 4 signaling effects, I tend to go with censored instead. Because that is baked into M+ Stata and other popular packages. So fewer choices, but possible is what I would say.
Or make your own.
Yeah, roll your own. There you go.
Yes. Yes.
Jonathan.
Yes.
Jonathan would say that, yeah.
He's making a guest appearance today.
You can use tan and you will be okay. It is like one of the questions in the event. One person was presenting about how to do something, and one of the participants asked how to do this, but not in JAX. And don't say stan
Yeah,
either.
that's what he said. How do I tell my psychology friends to do this if they don't use JAGs and don't say stan?
Yes, yes, exactly. That was great. Because I thought about stan too. Okay, so then about can we do this with latent variables, with latent outcomes? And yes, we can. We can perform multi-level analysis with latent outcomes, and that's known as multi-level structural equation modeling, or MSEM. Lisa had some of those models for the advanced longitudinal class. So yeah, we can. We don't need to observe outcomes only. We can work with almost any type of variables, and that's within the same framework. For instance, now I've been trying to learn how to do multi-level measurement models. In those cases, we also have multi-level analysis because let's say that we want to measure something like classroom climate among students. We know that students are nested in classrooms and are nested in schools. So we have that hierarchical structure, but in this case, our outcome, like what is classroom climate, it is a perception. It is not directly observed. In those cases, we can use something from the SEM framework. Then power and sample size considerations, and this is related to a question about how to know what sample size we need and with which power. In this case, I think that we could use something like the design effect to calculate or to have some estimates about power and sample sizes. We cover design effects and effective sample size in lecture 2, in case you are interested. Finally, how this centering discussion works when we have more than 2 levels. Because remember that we will have as many levels as sampling dimensions we have. So we can have multiple levels. What can we do when we have, let's say, a 3-level model? Well, it is the same that we have been doing here. We will be working level by level, and we will have different level-specific effects. So if we are using, let's say, cluster mean centering, at level 1, we will be centering our level 1 predictor at the cluster mean of that predictor at level 2. If we have in the level 2, if we want to use cluster mean centering, that level 2 predictor will be centered at the cluster mean at level 3 of that predictor. Now you are like escalating things level by level, okay? And in a 3-level model, we can also have cross-level interactions, and you must pay attention to the potential smooshed effects too. We can have random slopes, let's say for a level 1 variable at level 2 or level 3, and for level 2 variables, we can have random slopes at level 3. And of course, we will have random intercepts at level 2 and level 3 at least. That will be like our primary model now because we have three levels. So centering in those cases works the same as here, level by level, or depending on what you are interested in. Because if you have like, if you are interested in contextual fixed effects, so now you will have, you can have contextual fixed effects at level 2 or level 3 for a level 1, and at level 3 for a level 2 variable. Okay? Questions? Doesn't make sense? To me it makes, but come on.
There's one thing I want to chuck out there and that I wasn't sure about. So
Yes.
when you go up level, you're only subtracting 2 with your centering. So like the 2 with the 3, and then you might do like a 4 with the 3, and then like a 5 with the 4 when you're doing your centering, when you're, you know, as you work your way up, you're not going to subtract off everything down below, like 5 minus 4 minus 3 minus 2 minus 1. It's only you're only doing the pairs that you are concerned about.
Yeah.
Although I do have a question.
Yeah.
What if, or maybe you can't, can you skip a level? I have no centering on level 2, but having on level 3?
Yes.
And so in that case, would you be subtracting something from 2 or no? Or you just be subtracting from the most recent level?
That's a tricky question. That's something that I would ask too. My solution, let's say that we have students in classrooms in schools, although I don't have enough information about schools or I'm not interested, but that would be weird, like dropping something in the middle and then trying to control for the things at higher levels. I don't know. What would you say, Lisa?
So, yeah, I can think of 2 situations in which you would want to do that, and it's related to the middle level thing.
Right.
So in the advanced longitudinal class in 23, I had time for a 3-level example, which was occasions within twins within a family. So
Yes,
same-sex twin pairs. And in terms of change over time, the twins entered the study with a 20-year age differential, and then they were followed up to 8 years. So time was both how old you were when you started and how long it's been that you've been in the study. So in that example, if I put in age as an outcome and I fit an empty model, it turns out there's no variance in age at level 2, only at level 3 and level 1, which makes sense because they're twins. Like by definition, right? They're the same age. So the only way you would have had variance at level 2 is if they were measured far enough apart in time that one was older than the other one when they were tested, but they tried to control for that. So in that example, I had time at level 1, which was the difference relative to your age at starting the study. And then I had the age at which they started the study at level 3 as the cross-sectional effective age, and then I had the longitudinal effective age at level 1. So I skipped level 2 entirely. As another example, there's a student in science ed whose dissertation is looking at changes in ISAC scores for science in 8th graders. And he has students at level 1 nested within essentially cohorts, like which year you were an 8th grader, nested within school districts. And in the demographic variables that he's controlling for, such as free and reduced lunch, which we'll see today, There's differences at the kid level, there's differences at the district level, but within a district year to year, there's basically no variation. Like it's the same proportion of kids who get free lunch year after year. So what I had him do is center free and reduced lunch at level 1 relative to the year and district specific mean. That way it's purely level 1. Nothing's going in at level 2, and then the district mean across the kids and years at level 3. So then we have district differences in proportion of students who get lunch, not year-to-year differences, but then we have within-year differences between kids in the same school. So yes, that's why it's imperative that when you first start an analysis, you crank ICCs for every variable that you care about, because you got to figure out where it has variance as a logical prerequisite for where it goes in the model. So if it doesn't have variance, it's not going to do anything at that level. So, does that help?
Yeah, thank you.
That makes sense. Thank you, Lisa. So, now let's cover the second part. Let me click here. Yeah, so this is the problem we had. A researcher interested in determining the effect of an intervention assigned to teachers on a student level outcome, such that 500 students are nested within 20 total teachers, a cross-sectional two-level design. They want to ensure that the intervention, denoted as group below 0 control or 1 intervention, is equally effective for students of different abilities, as measured by a separate covariate called ability that was standardized to have a mean of 0, and so they fit this model. And here you can see the model in its data, R and R. Imagine you are reviewer 2 for a manuscript reporting their study results. Describe the problems with this model with respect to each of the following 3 areas and how the researchers should fix them. Also provide the code for the revised model. So we have 3 aspects here, 3 things to discuss: estimation, fixed effects, and random effects. Okay? So here I have some questions for you related to each of these aspects. First of all, in terms of estimation, ML versus REML, does it matter here?
Yes.
Yes, yes. Why does it matter?
Because I saw someplace that said, don't do this without Dremel.
Don't do this.
I'm quoting Lisa, do this with Dremel.
Use REML. Why?
I'm joking, the ML, we need to buy this mission for random effects. Right?
Yes, exactly. What's the problem? What's the word that you will use to describe that bias? What's the direction, sorry? What's the direction of the bias?
Too big or too small?
Yes. Too big or too small? What happened to variance estimates with ML, especially in small sample sizes? Too big or too small?
Too small.
Yes.
It's too small, but it makes a break.
Yes, they are too small compared to what they should be. Why? Because in ML we are not accounting for the uncertainty that the estimation of fixed effects involve. Here you have an image. This comes from Lisa's book in chapter 5, and I recommend you chapter 5 if you are interested, like in how fixed effects, random effects are estimated, and what the difference between ML and REML are. In chapter 5, I think it's pretty good, and also you can read chapter 3 by Enders in Applied Missing Data book. Those 2 sources I think are very good to understand differences between ML and REML and how do they work. Now, specifically for the case of the difference between ML and REML, you can see here that as the number of persons increases,
So
that
this is people are level 2.
exactly, that here,
It's like clusters.
yes, because this is for longitudinal data. So in longitudinal data, we have occasions at level 1, something like repeated measures. Let's say you are measuring the same subject multiple times, and at level 2 you have persons. For our context, occasions at level 1 would be whatever your outcome is or wherever your variable is at level 1, and at level 2, instead of clusters, we have people in this chart. So here you can see that the REML estimates to be 100, right? The ML estimates, variance estimates, tend to be small compared to REML when we don't have a large sample size at level 2. So you can, and K is the number of fixed effects, because remember that one of the components of Dremel is N minus K in the denominator. So, but in ML it's just N. So that's the difference between ML and Dremel. That in Dremel we are accounting for the fixed effects that are being estimated. So here, as the number of fixed effects increases, so we have a more complex model, K equals A for fixed effects. You can see that we need more people to try to get that variance, the true variance that was said using Dremel. So that's interesting because at the end, ML doesn't correct its estimates for the uncertainty, and they can be, they will be smaller than they should be. That's the issue. And especially in this case, because they had 20 teachers at level 2. That's small sample size. Although you can read in some books that simulation studies, I think, suggest that 50 could be okay. I think Snyder's and Bosker recommend at least 50 units at level 2 to compensate the difference between ML and Dremel. But based on this plot, you can see that depending also in the number on the number of fixed effects, you can need more sample size at level 2. So instead of using ML, I think that Dremel would be safer for your results. That's the takeaway of that plot. Then about fixed effects, what does the fixed effect of ability in our model is right now? Based on this model. Yes, based on this model. What's this fixed effect? In theta is that one, in R is this one. What is that? How would you call that?
What does it mean? Is that what you're asking?
What does it mean? What's the interpretation? What would you say about whatever that fixed effect is? Smooshed. Yes. Why smooshed? Why would you say that? Just looking at this, without looking at model results, numbers, just looking at this formula.
You're putting it in the model, assuming it's a level 1 variable, but in that model, how it is right now, it's also accounting for level 2 variance. If there's any in that variable, you haven't clustered it or anything to partition that variance.
Yes. Let me ask you this. How would you know that that can be the case? How would you know that this level 1 thing could be a level 2 thing too? What will you show me to convince me that that's the case? The ICC of what? The outcome or the predictor? The predictor, right? Yes. Yes. So in that case, from the beginning, even after trying to fit a model like this, just with a random intercept only model for the predictor, we could have an ICC and we could have an idea about the systematic variance of that level 1 predictor across clusters, and we could know that that level 1 thing could be a level 2 thing too. If that's the case, what we could do? What's the answer? What we could do? What we could do so? How can we solve this?
Now we can create two a variable probability within a variable probability between.
Exactly.
We are accounting for.
And that between thing, what it is? What it is that between thing? What it is? It is something like a cluster median, something like a cluster mean. What it is? What is that level 2 thing that we should have here? What it is that level 2 thing? Just cluster means, yes. How is when you say these are like easy balls? No.
Softball.
Softballs. These are softballs. Come on, I'm not trying to judge anything that you say. So yeah, we can include the cluster mean of ability to as a level 2 predictor. In that case, we solve one thing. What are we solving? The smoothed effect or conflate a fixed effect for the level 1 predictor for ability, right? Now, is that enough? Based on the context we have, because remember that for this thing, we are also trying to see if they want to ensure that the intervention is equally effective for the students of different abilities. What does it mean in terms of the model we are trying to fit? Right now, well, not right now, but the level 1 fixed effect, the within cluster fixed effect of ability, after having included the cluster mean at level 2, that will be a within cluster fixed effect, right? What's that fixed effect for the clusters? The same for every cluster or can differ across clusters? They can, but that's related to a random slope. Now that I'm thinking. Let me, yes, let me rephrase myself. How can we know if that fixed effect is moderated by the group variable? How can we test that? What can we include in our model to see if the level 1 predictor can be moderated by our group variable? What type of interaction? A cross-level interaction, right? That's what does the cross-level interaction is doing in the model. We want to see if the within cluster fixed effect of ability varies across the values of group. In this case, we only have 2 groups, so we want to see if different groups can have different values for the level 1 fixed effect. And that's something that we can do adding a cross-level interaction in our model. Now, this is for fixed effects. If it is sufficient, no. Okay. If not, what else is needed? So we need our cross-level interaction. But how can we fully separate the fixed effects in the reference model? We added a cross-level interaction between ability and group. Great. Is that enough to unconflate or unsmoosh all the fixed effects in our model? Let's say that right now we have a within cluster and a contextual fixed effect at level 2 because we are not using like cluster mean center of ability of level 1. We have ability of level 1, the original variable, and we have its cluster mean at level 2. And we added a cross-level interaction between group and the level 1 ability variable. Is that okay? Are you happy with that? What do you think? And I think that the model would have helped here, like piece by piece, adding things.
Yeah, can you go back to the code for a second?
Yes.
Let me ask it a different way, right? We agree that this is smushed, right?
Yes.
Is this one smushed then? Yeah, how do we fix it? Y'all got this right?
Yeah.
Oh,
You
add a right, okay.
So you would just add another interaction term to your equation with the cluster mean centered variable ability.
That's one option. I think that, yes.
You got two choices, yeah. You can keep ability like this, in which case you would add the interaction with the cluster mean. And
Yes.
that would be a contextual interaction. Or you could switch your parameterization to cluster mean centered, and then you would be adding the between interaction. But,
Yes.
yep, either way.
So we have two options, and that depends on which centering scheme you are using. Remember that cluster mean centering and constant centering are likelihood equivalent or analytically equivalent, so you can get the same results using any of both options, cluster mean centering or constant centering. So as Lisa said, in this case, we could use something like the cluster mean version of ability at level 1, and with group at level 2, that cross-level interaction would be unconflated or unsmooshed. Why? because the level 1 variable would be the purely within cluster component of the level 1 predictor. However, if we are using this ability, let's say with constant centering, we can have any number there. This interaction would be smooshed. Right now it's smooshed. So to unsmoosh that interaction, we need another interaction at level 2 using the cluster mean of ability and group. So doing that, this cross-level interaction will be like the level 1, will have the level 1 component controlling for the other interaction with the level 2 component. Two. Oh no, it's only one cluster mean in your model. Yes. You mean that there will be two interactions? Yes, yes. We will have two interactions in our model. One is cross-level. This will be the cross-level interaction. The other will be an interaction at level 2. So in that case, the interactions are controlling to each other. Guess what? The interactions, we will have the cross-level interaction, and we will have, let's say, the level 2 interaction with the cluster mean ability. We can get something like the contextual and between interactions, depending on the centering scheme we are using. That's in example 3, I think.
Example 4. That's
4.
We're heading into that territory.
Yes.
Yep, and I'll point out that I deliberately made this vague because this is what I'm used to seeing in practice. Equally effective for students of different abilities. It doesn't say the within school effective ability or the between school effective ability or the contextual effective ability, just ability. So do you want to know if students within a classroom who are relatively better at something benefit less? Or do you want to know if classrooms who differ in composition of students and abilities, like if you have a high ability classroom, do they benefit less or more? Like those are different questions. So moderation happens at both levels potentially.
Yes, yes. And that's another thing, because remember that interactions can be interpreted in different ways depending on what predictor you are using as a reference. So in a two-way interaction, you will have at least two different interpretations, because x1 can moderate the slope of x2, and x2 can moderate the slope of x1. You can read in interactions in both ways, and that's part of homework, the last homework 3.
Oh, is it? Okay, good.
Yes.
I think so.
In those, you will realize that you can interpret the same number, the same interaction in two different ways, depending on what you are using as the primary reference.
That sounds familiar now. I'm with you.
Yes. So that's that part. So this would be the final recommendation. Like, please check for the potential smooshed or conflated main effect of ability at level 1 and the potential smooshed or conflated cross-level interaction in the model. Finally, for random effects, let me ask you this. What component of variance do cross-level interactions usually explain?
I'm gonna guess one. I'll pick you wrong. I can guess and have had sound in the room.
What component of variance, what random effect variance should be reduced by a cross-level interaction? The variance of what would be reduced by a cross-level interaction? The random intercept variance? The residual variance? Random slope variance? What do you think? We already know that fixed effects help us to explain things, right? A level 2 fixed effect will help us to explain or reduce the random intercept variance. Are you sure?
No.
But that could be.
Yeah, we're talking about that today.
Yes, that could be.
That's one possibility.
Yes, but not mainly. Yes, not mainly. Let's say that.
It could be, but it's more likely to be for the.
Another thing first. let's say in second place that could be the case, residual variance. But in first place, what a cross-level interaction could help us to explain, understand, or interpret? What should be reduced after including a cross-level interaction? That's a variance component. So in this model right now we have three: residual variance at level 1, random intercept variance at level 2, and random slope variance at level 2. Those are our three variance components. The cross-level interaction, what should reduced in this model? What would help us to explain? If we know that the within cluster fixed effect of ability, let's say that differs across groups, what should be reduced?
If it's a cross group, it should be the slope.
Exactly, the random slope variance. So whatever we had before the cross-level interaction should be reduced after including the cross-level interaction. Why? Because we know that part of that variation in the within cluster effects from cluster to cluster could be explained by the cross-level interaction. Because we know that group could moderate or moderates the within cluster fixed effect of ability at level 1. Okay? So it is same logic as we have seen before. Level 1 things will explain residual variance, a student to a student variation, let's say within a classroom. Level 2 things will help us to explain some of the level 2 things, or purely level 2 things will help us to explain cluster to cluster variation in the random intercepts. And cross-level interactions can help us to explain a cluster to cluster variation with respect to level 1 fixed effects, within cluster fixed effects. Okay? So this is our final statement. We are missing a random, well, you should say. We are missing a random slope for ability at level 2. And remember, please, that conflation is also a thing for your random slopes. So in this case, to make things easy, we will be using the within cluster version of ability to capture purely slope heterogeneity. Okay? This means that we were assuming that the within cluster fixed effect of ability was the same across all clusters. After including the random slope for ability, we will have two new parameters in the model, which are, what are those two new parameters after including the random slope? We had one random intercept, we added a random slope. What are the two new things in the metrics at level 2, the G metrics or T metrics? Yes, exactly. Random slope variance and the covariance between the random slope and the random intercept. And I have a bonus question, and I had some kind of prize, but I couldn't bring it. I have some chocolates for the person who asked. Yeah, this is a softball. But how will you test whether including this random slope significantly improves model fit? Likelihood ratio test, yes, exactly. And that's our correct models.
So pause on this, I want to read.
Yeah, so here, basically what we are doing, we are using the within cluster version of our variable at level 1. We added the cluster mean ability. Why group is the same thing as before?
Another bonus question.
Because group is a truly level 2 variable, you don't need to center anything.
Exactly, yes. Yes, group is a level 2 thing. We have not talked about that because it is what it is. Then we are using, you can see here, this cross-level interaction using just the within cluster version of ability, and we are including this here. Is not needed to unsmoothed fixed effect, but that's part of the story. Okay? So you can consider adding both interactions in your model just to see what the whole picture is. But adding this cross-level interaction would be enough if you are only interested in the moderation of a group on your within cluster fixed effect of ability. And remember that if you don't include something in your model, you are assuming that's 0. right? Anything that's not included in your model will be assumed 0. So in this case, for instance, we are also assuming that whatever the random slope for the level 2 would be is 0. But that's not a problem most of the time. Okay, that's all. So, questions? Wow, 45 minutes. Sorry, Lisa.
It was good discussion.
Awesome, thank you. And remember, please, if you have more questions, you can email us or you can attend office hours and you count on us.
Yes, indeed. Thank you. Okay, as promised, I'm going to get paint out for a moment. Random intercept and slope correlations. That's what I wanted to draw here. Okay, so this is where random slope confidence intervals come in handy for you to figure out what your pattern is. Because if you have random slopes, that could look like this. Like all the clusters are going up just to different extents. Could also look like this. All the clusters are going down, but to different extents. Or you can imagine situations where you've got some of both, right? So you have to think about these slopes as a rank order of people to think about what the correlation means. So let's say that you're over here in this situation, and you have a positive correlation between the intercept and the slope. Then that would mean people who are higher at wherever 0 is, or excuse me, clusters, wrong class. Clusters who are higher at wherever 0 is on this axis tend to have more positive slopes. A stronger effect would go with a higher point at 0. A negative correlation means clusters who are higher at 0 would have a shallower slope. Okay, so that version works. Now this one. A positive correlation means as the intercept is higher, the slope is higher in terms of rank order, but what high is shallower. So higher intercepts go with shallower decline if the correlation is positive. Higher intercepts go with steeper decline if the correlation is negative, because those are the lowest people in the rank order of what the slope is. Or clusters, damn it. It's like you triggered me like bringing up this thing in my book. Now my brain is broken for today. But clusters, we're in the clustered class. But does that help at all in terms of how to think about it? And what Bladimir said is true. I rarely see those correlations interpreted. One of the things to keep in mind is that it really does depend on where 0 is. So if 0 is here, you may have a different rank order than if 0 is out here. So your intercept is conditional on that 0 point. A higher cluster would not necessarily be higher at a different point on that axis because non-parallel lines eventually cross. So it's somewhat arbitrary what correlation you end up with because it changes with centering. So I don't tend to make a whole lot of deal with that. What else was I going to say about that? I think that was the only thing I was going to draw. So I know this is still a lot. Don't feel like you need to understand everything related to cross-level interactions and random slopes just yet. It's going to keep sinking in as we go through here. Your next formative assessment is ready. Erica's going to be doing that one. It's the same one you did 2 years ago. It's multiple choice. So the way it's going to, see? People like multiple choice. The way it works is I'm describing a model and then I'm going to add this to the model. And for each variance component, what should happen? Stays the same, goes up, or goes down. So it's trying to get you used to the idea of thinking about every fixed effect in a multi-level model has a job to do. And you got to identify what should happen, at least in an ideal situation. So I've set it up so you can't see your answers. It's going to be a surprise, but I'll turn them on. I know. Tuesday morning, once everyone's turned it in, or we're going to go over it, I will make it so you can see what you got wrong, and we'll go over it in the same way. And I would highly recommend writing out equations. I know that sounds painful, but it will help. Because a guiding principle to figuring out which variance component is being explained is that it's the one in your equation. Like that's just the default. So let me go through a little bit of that in terms of the examples that we've been talking about. So slide 5, let me pause here for a second. We're just going to hit sort of like a highlight reel, if you will. So in this example, I have one predictor, and I have a within cluster version and a cluster mean version. Okay, it doesn't really matter what it is for the sake. In this slide, I am making the point that this is the new term right here, U1. That's a random slope. So together, when you add these two terms together and create beta 1 is the within cluster effect of this predictor, specifically for cluster C. And the specifically for cluster C is important because now this term implies that it could be different. If it's just a fixed effect, it's literally a constant. Like everybody gets the same slope of 2 or whatever it was estimated to be. U1s are deviations. And we do not care about the individual values. They're not actually part of the likelihood. What we care about is their variances and then the covariances. So conceptually, we've created a new cluster level outcome. Why is it that some clusters have a stronger effect of this within cluster X variable? Cluster characteristics have to explain that. That's what a cross-level interaction is for. Let me get a slide that has one of those, I think. Here's one. So this is slide 15. So what's been added is highlighted in yellow here. Now I've added, stop it, the cluster mean as a predictor of the within cluster slope. So this could be any level 2 predictor. It doesn't have to be the level 2 analog of the predictor. That's just like to keep the story simpler. So what this is saying is that part of the reason some clusters would have a stronger effect of whatever this is depends on their average for that variable. And then U1 becomes a leftover type of random effect. Why is it that some clusters still have a stronger effect of this predictor even after you control for this characteristic? So the job of a cross-level interaction is to explain the random slope variance of the level 1 predictor that's in that cross-level interaction.
So you're reducing U1C.
Exactly. Now, if I had another predictor in here, let's say this is like WCX2, and I put in an interaction, it's not going to explain this because that's not what it's focused on. Like it's a different slope that we'd be talking about then. So if we have a random slope for this level 1 predictor across level 2 clusters, we can then input cluster level predictors to explain that random slope variance. That's what we're doing. Now with the situation we have not yet talked about is what if this is not here? Then what happens?
Are you, if that's not there, I'm just gonna guess, are you assuming then that all the slope change is either the constant or the other part with based upon which center you're on?
I don't think I understood. Can you please try again?
The only reason that the slope is changing is because of the first two terms. There is no leftover. That's the assumption of it.
Yes, exactly. That's where we're headed. If this is not here, you are saying the differences between clusters in this level 1 slope is entirely due to this thing, and that is it. That's the only reason. Otherwise, they're the same. That's a very strong assumption. It's very testable, fortunately. But that is the situation that one can find themselves in. And that's what I wanted to talk about. I think we've gotten through a lot of this stuff, but not that. Okay, so new stuff starting on slide 38. So same equation here. So the question I want to ask you is, can we still examine this cross-level interaction or any other with this predictor if U1 is not here? This is actually somewhat controversial. This would arise in the situation in which you start by testing whether this random slope is needed in the first place, because that's a logical prerequisite. So let's say that you find it's not. It's not significant, doesn't help the model, looks like clusters don't really vary in their effect of this predictor. Can I go ahead and still test this cross-level interaction? Like if this is your primary research question, it doesn't make sense to be like, sorry, can't answer it, I don't have a random slope. Like in practice, you're going to want to do something to answer your question. However, some folks would say, nope, you're done. game over, do not pass go, do not collect $200. And the logic behind this is if a level 1 slope does not vary randomly over clusters, right? Every cluster gets the same, then why are you trying to predict variance that doesn't exist? Like, it's functionally a constant. This is not going to work. And to the extent that there is any kind of random slope variance that's there, even if it's not significant, that will result in standard errors that are too small for the fixed effect that the random slope is for, as well as any cross-level interactions involving that random slope variable. And degrees of freedom for the denominator are estimated at using level 1 sample size rather than level 2. So folks who say if U1's not there, you're done. That's one perspective. The alternative is found in a couple different textbooks, Snyder's and Bosker included, and they wave their hands and say, well, the power for random slope variances is often lower than the power for fixed effects, so you could end up with something like this, and it's a type 2 error, essentially, that you don't keep the random slope. So if you agree that this is viable as an option, then you need some new vocabulary to describe the situation. The new vocabulary is systematically varying, or non-randomly varying. And note with my colors, I have fixed effects that are in red and random effects that are in blue, so I made this purple. Because it's a blend, you see. So it's like Goldilocks and the Three Bears. Like, you know, we have like the mama bear's like chair that was too soft and the daddy bear's is too hard and the baby bear's was like just right, that whole thing. It's kind of like that. So fixed is every cluster gets the same. Random is every cluster gets a different slope. Systematically varying is they get a different slope according to their standing on this predictor, and that's it. So the slope doesn't vary randomly, it varies systematically. So when you would come to this conclusion, I've got some scenarios here. The rows are telling what happened with respect to testing the random slope variance in the first place. So if you initially tested a random slope variance for this level 1 predictor, and what was found to be not significant. So looks like clusters don't need different slopes. You then nevertheless go ahead and put in the cross-level interaction between, say, group and your level 1 predictor. Now in this scenario over here where it's significant, we would say that the effect of this predictor is now systematically varying. It depends on what group you're in, but it doesn't vary otherwise. So each group would have a different slope, but within a group, the clusters are homogeneous in their slope of this level 1 predictor. That's what this would mean. If the interaction was non-significant and you dropped it, then we would keep the same language that the slope is truly fixed. It's the same for every cluster regardless. Okay, with me so far? All right, so what if you did have a random slope? You added a random slope and its covariance with the random intercept to the model. Likelihood ratio test says yay, you made your data taller. But then it became non-significant after you added in this interaction. It could go literally to 0, or it could just become very, very small. If that's the case, you win. You win. Do you know why? Because you explained all the variance. If you had variance to start with in the slope, and you put in a moderator that explained it all gone, you win. It's like an R-square of 100% for your random slope. That can happen. I've seen it happen. It happens more frequently if there's not that much slope variance to begin with, right? It's a low bar, so to speak. And I have dots over here because this combination wouldn't happen. If the cross-level interaction does not contribute to the model, it would not have explained the variance away. And then down here is the situation in which you did have a random slope initially. You put in one or more cross-level interactions to explain it, but the random slope is still there. In that case, we would still use the word random to describe the slope because it's still varying for unknown reasons across clusters even after we put in cluster characteristics to try and explain why the slope is random. So there are 3 scenarios, basically. The slope is the same for each cluster. That's truly fixed. The slope varies across clusters for reasons we don't know. That's random. or the slope varies as a function of a level 2 predictor only, and that's it. So these are the more controversial of the two. So summarizing in terms of what's possible, there we go. So then in terms of explained variance, I go back. Do I have that? Oh, I have words. That's what I have. I want the equation. That's what I want. If U1's not here, this breaks the rule of the fixed effect explains whatever variance is in its equation. Well, if this is not here, where's beta 1 going to go? Here. Now it's explaining E. So if there is no corresponding random slope for the level 1 predictor in a cross-level interaction, that cross-level interaction has to explain level 1 residual. Has to. That's where it came from in the first place. I have, yeah. Pictures. That's coming. All right. So here are all the words, basically the rules that I'm looking for you to demonstrate an understanding of in next week's formative assessment. Here they are. Yep.
Random guessing.
No random guessing. You get your 3 points regardless, right? There's no reason not to try. Fixed slopes of level 2 cluster predictors by themselves. So between cluster main effects or interactions. The interaction among 2 level 2 predictors, for instance, that's what I'm talking about. Either the main effect or interactions among level 2 predictors explain intercept variance. If you have a cross-level interaction, then it explains the random slope that goes with the level 1 predictor if it's there, or it explains residual variance if that random slope is not there. And you need to have evidence that it is not there to start with. Yeah.
What if both are there?
What do you mean both are there?
So if you do have a random slope and, oh, never mind. I don't know. My brain just said no. Go ahead.
Your brain just said no.
Yes.
Okay.
It just said no.
Okay, fair enough. I'm just noticing I have a plug that's not plugged into anything, and I'm wondering what I missed in my step.
The mic?
Oh, the mic is on though. It must be using
Maybe
this
it's
mic.
using your computer mic.
That's what it's doing. Okay, yeah, because it's not green. So yeah, this is not plugged into here. That's the step I missed. Well, it's still, fortunately, it's green, so something's recording. We're going to go with that. Anyway, I'm sorry, lost my train of thought. What did you say?
It doesn't matter. Go forward.
Fair enough. So if this is the situation, you don't have a random slope for the level 1 predictor that you're trying to moderate, it explains residual variance, and you would call the level 1 fixed effect systematically varying, not randomly varying otherwise. So, and then for level 1 person predictors, what happens to their variances depends on how they are put in the model. So if you have a level 1 person predictor without level 2 variance, what does that mean? What would you have done to accomplish that? How do you have a level 1 predictor without level 2 variance in it? How do you make a level 1 predictor that does not have level 2 variance in it?
With it plus
Cluster mean centering, yes. You subtract out the level 2 variance, literally. So if you've used a cluster mean centered level 1 predictor, then its main effects or interactions among level 1 predictors would explain level 1 residual. If they do have level 2 variance, then they will also likely explain the level 2 random intercept. However, if the between and within fixed effects are sufficiently different, it can actually make the intercept variance go up instead as a model misspecification. And intercept variance will go up anytime level 1 residual variance goes down. So what happens after level 1 is a little bit trickier, but those are the general principles.
Can you repeat that last
Yeah.
one again, please?
Yes. So if you have a non-cluster mean centered predictor, like you left it alone, it has level 2 variance in it, the smushed effect that it would be given simultaneously explains level 1 residual like it was supposed to, but also level 2 random intercept that it wasn't supposed to because Trojan horse. Okay. If the between level effect and within level effect are sufficiently different and you smush them together, you actually could make your intercept variance higher because you're putting in a fixed effect that's straight up wrong as opposed to zero, like you're making it worse. I've made that happen in simulation before, at least, to prove the point. So if you have a level 1 predictor with level 2 variance in it, it kind of depends on what the smushed effect is to know what's going to happen to the variance components. That's what I would say. All right, so intermediate summary, words of everything that we've said here. I'm not going to read the slide to you. That's going to be a bingo square, by the way, the next time, is reading the slides to us directly without elaboration. Also, animation fail. I'm going to add that one too. That's a good one. All right, so this is the picture that I wanted. Once upon a time, we had a box, right? It's a square, yeah. It's a green and purple square, because you know where I'm going with this. So we had all the variance in y in one pile. And the first thing we did was take that pile and split it into two. So we have what I'm calling level 1 within cluster residual variance of the e's, so across the people, across the clusters. We have level 2 between cluster intercept variance of the U zeros, so this is variance across clusters. It's purely level 2, that's the green. Then we can add fixed effects, and this is meant to be sort of a Venn diagrammy thing in terms of which variance is explained by that. So the within cluster effect of a predictor would explain some of the residual variance. The between cluster version, so this could either be a contextual effect or a between effect, take your pick, will explain this variance. So far, so good? Okay. Now we also might have slope variance. It's possible that the effect of within cluster X varies across clusters. Now where does this come from? It comes from E. So E conceptually was all the reasons why people from the same cluster still differ relative to one line for a fixed effects that all the clusters share. Well, it's possible that some of those people differences is because the cluster line is wrong for that cluster. It needs to be this kind or that kind. And so what we were calling people variance is actually could be cluster variance still. That's sort of lurking in there. So when we pull that out, the definition of residual changes relative to what it was before in terms of the information that it contains and what it is residual from. So because this slope variance was in here to begin with, if this is not here, any cross-level interaction would explain the E variance. So the intercept variance moves down, the slope variance would be here, and because these two things are both cluster things, I'm out of words, they get a covariance. Cluster variables, how's that? So any cross-level interaction involving within cluster X would explain this slope variance right here. A cross-level interaction involving some other predictor that's not on here would explain the residual, because it doesn't have a random slope yet. Ta-da. Yeah, that's what I said. No, not today. No.
Just no.
Well,
Plus time.
am I right?
Ooh.
Yeah, no, not today.
Ooh.
Yay, matrices, said no one ever. Yeah, no, we're done for today. We'll pick this up on Thursday. We got more to go. My guess is that I'm not actually going to do this in front of you. I'm going to put up a video from last time when I did it, because it will go better if you have a pause button so you can walk away and like get it out of your head. All right, so then, let's see. Everybody has their marching orders with respect to your projects, right? Everybody knows what they're doing? And the next thing due is a check-in in a few weeks. Formative assessment due Monday. Let us know if you need anything, okay? No, it's in the next week, the 10th. Yeah, the next homework is not due for a while. It's hard. Start early. So, just telling you. It's the last one, so it's got to be like the grand finale of homeworks.
I saw it's Monday. I was like, no.
Not this Monday, no. All right. Thank you, folks. See you Thursday.